Great. Okay. So last time we talked about Nash equilibrium and how we can compute Nash equilibrium. So essentially, that's the thing that we talk about, the complexity of finding Nash equilibrium, and we gave algorithm that in certain cases we can actually solve the problem. Here we want to talk about some relaxed version of Nash equilibrium called Epsilon Nash Equilibrium. This concept of Epsilon Nash, you can actually consider it in lots of other games or other solutions when we have epsilon dash something. And then we will talk also more about some other, I will say, heuristic ways or the way that we can actually simplify the normal form game and have even faster algorithms for Nash equilibrium. Because as we discussed, the problem is still we don't have a polynomial solution for it. But the idea is that maybe we cannot solve it in polynomial time, but can we still write fast algorithm for it? Good. But before that, let's talk about epsilon Nash. This is an important one. And this is like a very practical way of seeing the problem. So the idea is that the people, we are assuming that the people are happy and they don't want to generally change their strategy if the gain would be very small. In other sense, there are some other essentially cost of changing your strategy. And this cost, we are assuming it is epsilon. So it is a small things that the people are happy. Okay, if there is also a little bit more, maybe I don't want to get it because I'm happy with the current situation. And anyhow, changing the strategy has some cost. So does epsilon be greater than 0? A strategy profile, again, a vector of strategies, and each of them is a mixed or pure general, is an epsilon Nash equilibrium if for every agent I and for every strategy S prime I not equal to Si, the gain that you will get from Si is greater than or equal to the gain that you get it from the utility that you will get it from Si prime minus epsilon. What's the meaning of that? In some sense, it means that the marginal that you will get it, like the marginal that you will get it from S prime. The marginal would be defined as ui of S prime of I S minus I minus ui of Si. S minus I. That should be greater than, that should be less than or equal to epsilon, correct? So if you write it this one, then that would be this, it should be less than epsilon. So this is called marginal. Marginal gain. So the marginal gain that you will get it if you change your strategy from S to S prime, from Si to S prime I for any S prime I is at most epsilon. So we know that epsilon Nash is the definition clear. Good. Now, epsilon Nash equilibrium always exists for any epsilon greater than 0. Why? Because there's a Nash equilibrium that exists. So if the Nash equilibrium exists for any epsilon greater than 0, of course, a Nash equilibrium also would be an epsilon Nash. However, we will see that the reverse is not essentially necessarily correct. So in some sense, I mean, we know that if you are doing, I mean, so in the Nash equilibrium, like for everyone, essentially, we know that you cannot get any marginal gain at all by changing the strategy. So it is epsilon Nash. And you can think about, I mean, some area near to that, surrounded by that, also still might be a, we don't know how big is that, but it depends on the game. But some area around it is epsilon Nash. So it is like more somehow continuous way of considering the Nash. So, I mean, one idea essentially is that, I mean, when we compute epsilon Nash, like in general, I mean, the Nash equilibrium by itself, when you are using computer to obtain it, I mean, they have some certain precision. So in some sense, even the one that you are finding by computers have these things that they are somehow bounded by the precision of the computer. In some sense, you can only find epsilon, not really the Nash. I mean, at least not in the general case. Uh, yeah, and in general, it seems that this is some kind of relaxation that hopefully you can find essentially epsilon Nash in a better way. However, this is another proof for that. That I mean, essentially that the people prove that finding an epsilon Nash equilibrium is still pipette complete. And that we discussed, pipette complete is not an NP complete, and we don't have so we have something like P here, pipette here, and then NP here. So NP like so we don't like potentially all of them can be equal that we don't know, but currently the one that we have pipette is something between P and NP. We will talk about it hopefully a bit later about the pipette in general. And yeah, so that is this pipette also has been used for other local search type of algorithms. And yeah, you can read more about them, and probably we will talk later in this course more about it. So even finding an epsilon Nash is pipette. So in some sense, the hope was that we can define this relaxed version of the problem, and we can find it in a more like efficient way. But unfortunately, even that we don't know that it is possible. So, but another interesting thing is about like the one other thing is that whether epsilon Nashes and Nash are like close to each other or it can be quite far from each other. Let's see this example, which is a good one actually. See an example. So as we discussed, for every Nash equilibrium, there are some kinds of epsilon Nash equilibriums which approximate it, or like they are close to each essentially. So each Nash equilibrium that you consider Nash, there are some kind of epsilon Nash approximated or very close by. But the converse is not true. There might be some epsilon Nash that nearby there is no Nash essentially. All the Nashes are very far from each other. So this is a new concept in some sense. And again, it might be different from Nash. The same thing that we had about the Pareto optimal solutions, that there also the concept, sometimes I mean, they have some intersection with Nash, but not all the time. It can be far from Nash. So let's see an example here. And we will talk about this IESDS just after this. This is a way essentially to simplify. So a way to simplify a normal form. Normal form for finding Nash. That we'll talk more about. But so consider this game. I mean, by these actions, player 1 and player 2. You can see that there is only one Nash equilibrium here, and this Nash equilibrium is dr. If you are 500, 500, I mean, if you are essentially, if you are doing that, the first player does not want to change it because it gets 0, and the second player does not want to change it because it gets essentially like 1. And you can see, I mean, that this is the only one because we can, I mean, as I mentioned, we can use this IESDS that we will just talk after this. And we can show that this matrix has only this one. Or we can, of course, compute it, all Nash equilibrium of that. However, you can see that. Yeah, and of course, as we discussed, because 500, 500, this is not only is a Nash, also is a Epsilon Nash. Every Nash is a Epsilon Nash for any Epsilon code. But if you consider UL, that is Epsilon Nash as well. So that is Epsilon Nash. Why? Because, I mean, if the first guy is choosing U, the second guy does not want to change it because it gets essentially instead of 1, it gets 0. But if the first guy is deciding to, the second guy decide to go L, the first guy also does not want to change it because it goes here to, from 1, it goes to 1 plus epsilon to the 2. And the marginal gain is at most is less than epsilon. So does not want to change. So UL is a Nash equilibrium, is an epsilon Nash here. And as you see, the payoffs here, the payoff that they are getting is like essentially by a large factor less than actual Nash equilibrium, like by a factor 500 essentially. This is something that we will talk also this session or the next session about price of anarchy, that you want to somehow give solutions that at least some of the payoffs are good essentially, are not very far from the optimum solution. And here, at least comparing even to the Nash equilibrium, there is one that gives 500, 500, but this guy only get 1 and 1, which is much less than that. This one. So Nash, and this one is not close to any Nash equilibrium, as you can see, because as I mentioned, the only one actually is 500, 500. So it is very far from Nash, and we can get it. This is the exercise. If you have done the project 1, it might be good to think about how you can do it. If somebody gives you an epsilon, how can you find epsilon Nash? This is, I mean, this is, you don't need to, I mean, submit the solution for this, but that might be a good way of thinking, that how can you also solve it for epsilon Nash? This is more like a research. You can read even papers and think about it. So how can you extend your algorithm for finding Nash to solve epsilon Nash? Of course, one way is to just find Nash itself. But can you try to, I mean, this is also a general thing. Can you try to find all, yeah, maybe this is the, as I mentioned, the more researchy thing. If there is an epsilon Nash which is far from Nash, can we find it or not? Just think about it. Good. So this is about the Nash and epsilon Nash. So let's go to this one and talk more about the other ways that we can simplify these games essentially. Good. So I mean, we want to continue with 2 things here. One is the dominant strategies. As I mentioned, that's something that you can use it to simplify the matrix and get essentially more efficient algorithm. It's more like a heuristic. Not always you can do it, but if it is possible, then you can get a faster algorithm. And possibly, actually, you want to implement this one in your project 1 as well. I mean, when you find a Nash, because that you can solve actually larger matrices, probably. And the other one is the price of anarchy, that this was related to this epsilon Nash thing that I have mentioned. And you want to somehow make sure that the payoff that you are getting, while in equilibrium, you are not very far from actually the optimum solution. Good. So let's define the dominant strategies. So assume that, I mean, Si and S prime I be 2 strategies for agent I. Strategies here essentially means, I mean, it can be pure or generally even mixed essentially, but say for now pure. We will discuss mixed as well. So we say that Si dominates prime I, if essentially I is doing better with Si comparing to S prime I, with with every strategy profile of S minus I. So in a sense, it says that like independent of like these are like two strategies that I have, independent of what other people are doing, always I'm better with Si comparing to S prime I. In that case, the whole idea is that if there is such a thing, then we can get rid of S prime I. And that's the way that we can use it actually. And you will see actually you can do quite interesting things, especially even when we consider the mixed versions of it. That you can do, I mean, some interesting things if you find this kind of dominant ones. And you can simplify the normal form matrix out of it. So mathematically, there are, I mean, these are the three versions of that. We always talk about strictly versus, I mean, weakly, or here in this case, even very weakly. So we will say Si strictly dominates S prime I if for every Si, the utility that you will get, the agent I gets, is greater than the utility that agent I gets. So if the agent I plays with Si gets more utility than the time that he or she plays S prime I. We say it weakly dominates it if it is always greater than or equal, and at least in one case, for one S minus I, you get greater. And finally, we will say very weakly dominates if it is just greater than or equal. So in some sense, I mean, I think all of them are making, all of them make sense, because you want to get strictly dominated, always is better. But that is maybe too much to ask. Weakly dominated is a regular one that is like essentially gets every time, but at least one cases it is you're better off. But very weakly it means that you are just not worth with the other. Yeah.
So does this mean that Si and Si prime could both be weakly dominant?
Yes, exactly. So the last one was this one. Actually, S prime I, because both of them are for I. You see, not Si prime. Si. Yeah. Yes. In that case, in the very weakly case, it means that it might be Si and S prime I that both can be very weakly done. Dominate each other. Great. Okay, so we talk about the dominant strategies, and this is the thing. So what? Let's see what can we do. What is interesting about it? These are, I mean, as I mentioned, these are some of this concept of strictness or weakly versus very weakly. We are defining it such that we get more stability, and these are exactly the solutions that we have, and these are very natural ideas. So these are like to say, okay, this is my strategy. For example, you may play chess and say, okay, if I do this, is strictly better than this other move, essentially. So that's a thing that is very common. So also, I mean, I mean, this is again some definition that a strategy is strictly dominant for an agent if it strictly dominates any other strategies of for that agent. So a strategy is strictly dominant if essentially if it is strictly dominates any other strategy for that agent. Good. Now, a strategy profile S1, S2, in which Si is dominant is a Nash equilibrium. Correct? By definition. Because we know that each of these S1s, S2, and Sns, each of them strictly dominates all other actions of this person. So it means that if you consider essentially a strategy profiles of these strictly dominant strategies, then it would be a Nash equilibrium. And you can actually say that it would be like if it is strictly dominant, then we get essentially a strict Nash equilibrium, or if it's the weak version, then we get a weak Nash equilibrium. So that strict and weak one also translates to that. Again, the idea is that if S1 is dominant, it means that S1 is my best option, correct? So independent of what others are doing. So what's the meaning of that? It means that like independent of any other strategies that these people taking, in particular this, S1 would be a better choice for me because it's dominant under any, for any S minus I. And of course, in particular, that this S minus I is this. So essentially, if we have a dominant strategies, they form a Nash equilibrium. Any questions? Okay. So I mean, this video is a nice one. I mean, you can actually talk about this kind of dominant stuff, and you can just go and watch it. I mean, it is somehow beyond the scope of the class, but you can actually watch this video. But let's see what can we get it here essentially for prisoner's dilemma. So again, the prisoner's dilemma is the one that this is the normal form matrix for that. So like consider agent 1, and this is agent 2. So for agent 1, D is strictly dominant. Why? Because consider this one. If you are doing, what is the other options that this person is doing? So if the other second player is doing C, I get it 5 versus 3. If if the other person is doing D, I will get 1 versus 0. So it means that D is strictly dominant. So in this case, D is strictly dominant for strategy 2, for agent 1. Similarly, you can say that D is strictly, this D is strictly dominant for agent 2 as well, exactly because of the same reason that I have mentioned. Because again, if you consider this person, so this second person, it gets 5 versus 3 here. If this person is doing C, and if this person is doing D, it gets 1 versus 0. So actually, in the dominant, this is like I said, this is a different view about this prisoner's dilemma. That if you think about this, so there is a dominant strategy. Always D is a better choice than C for each of these agents. So what's the meaning of that? Because of the thing that I have mentioned, then in this case, DD would be a strictly dominant strategy. And it is strict because the choices that you have are not equal, like 5 versus 3 and 1 versus 3, 1 versus 0. So in this case, we have DD, which is a strictly dominant strategies. That it is here. 1, 1. And as discussed, if we have a strictly dominant strategies, then they also form a strict Nash equilibrium, because any other option you will lose. Great. So we talk about this kind of dominant strategies and strategy profile, which is a vector of essentially dominant strategies, and of course its relation to Nash equilibrium in general. Now let's see how can we use it for further. This is another example. Let's go through this example and then we say how we can use it actually to compute these ones in a better, compute Nash equilibrium in a better way. Good. So if you consider the matching pennies, and by the way, these games are again very important to know because these are some kinds of, it seems very simple games, but in some sense they are trying to model several real world scenarios. And you will say, oh, this scenario is very similar to Pearson's dilemma, or this one is very similar to matching pennies, or this essentially from which side of the road. So is this matching pennies? You can see that here, now there is no dominant strategies. Why? For example, if this person is essentially deciding to go with heads, so this is agent 1, this is agent 2. So if agent, say 2, decide to go with heads, then he knows here, yes, if the agent 1 gets head, it gets 1, but if it switches, it gets minus. If agent 2 go with heads, then in this case, he's getting -1, while like if this person is doing tails, then it gets 1. So this means that this essentially head is not a dominant strategy. Now, what about here? What about if it goes with tails? If this goes with tails, essentially, then you can say that if agent 2 goes essentially by tail, then here it gets 1. But if this person changes it essentially from head go to tail, then it gets minus. So it still is not like the dominant strategy that because it depends to whether the other person is doing head or tail. You can do similarly for agent 1, and you can see that in this case, agent 1 or agent 2, none of them, because it's like a very symmetric game. There is no dominant strategy, and of course, then there is no Nash equilibrium in dominant strategies for matching pennies. The same thing also happens for which side of the road. For example, if you consider which side of the road, if you consider this person is doing left, then in this case, if this person is doing left, then he's getting 1 essentially here. But if this person is changing to right, then it gets 0 essentially, which is not necessarily, a dominant strategy. Good. So these are some more examples of this. So you can see, so it's very similar to this matching pennies. Actually, you can see that this one also does not get any. There is no dominant strategy. Again, the dominant strategy is the one that I will choose SI independent of the other person. Always I am essentially getting the best option if you compare this one versus the other options. And here, for example, as I mentioned, so here is taking left essentially. If he's taking left, this person is changing from left is good. But if this person changing to right, then in this case, if I do right, I will get 1 instead of 0. So it means that left is not a dominant strategy. The same thing you can say right is not a dominant strategy. Because if I doing right and this person is doing left, if I switch it from 0 to 1, then I can get a better result. Good. So that's about. So some games they may have dominant strategies, but not every game essentially has. And this is the important thing that actually you may want to consider, and we can check. Let's go to the good. So now let's use this concept of dominant strategy. So we talk about Nash equilibrium and Nash equilibrium of dominant strategies. That actually you may hear a lot. It is the case that if everyone is doing just a dominant strategy, then we have a Nash equilibrium. So that would be essentially, I will say it's too good to have it all the time. As we have seen in Prisoner's Dilemma, we had it, but which side of the road or matching pennies, we didn't have such kind of dominant strategies. A dominant Nash equilibrium. Or Nash equilibrium of dominant strategies. But another thing that we can use it is, now let's consider about, so far we talk about dominant ones. Now let's talk about the dominated ones. What are the benefits that we can get from this? So here, a strategy SI is strictly or weakly or very weakly dominated for an agent I if some other strategy S prime I strictly, weakly, or very weakly dominates SI. So in some sense, we will say S prime I is better than SI. Good. So here we have this considered dominant, and then now we talk about the dominated. So this is the main things about this kind of dominated one. A strictly dominant strategy can't be a best response to any move. Why? Because there is another strategy which is better than dominates it. Like SI cannot be the best move. Why? Because S prime I dominates it. And that is by definition that in every other strategy profile of others, S minus I, S prime I is greater than or equal to SI, the utility that you will get. So SI cannot be the best strategy. So it means that it can be removed from the matrix when you try to find a Nash equilibrium. And actually you can do this one in iterative way. So you can just eliminate those strategies which are useless in some sense for the Nash equilibrium at least. And then you will continue until you have a much simpler matrix. The size can be much smaller, for which you can find actually a Nash equilibrium. So as we discussed, this is like the number of strategies if it's even two-player game. If each of these players have n strategies, the running time would be 2 to the n, essentially, the best one that we have, because we need to consider all possible supports. But here, in this way, actually, we can remove them and we can get a much smaller matrix that for which we can solve the problem much faster. So this is some kind of heuristic that you can use it on top of the algorithm for any Nash equilibrium to find it essentially. And as I mentioned, this can be essentially, this gives the reduced form. And these other strategies may now be strictly dominated, even though they were not dominated before. So you can repeat these things or iterate until you will get the result that you want. So this is the method called iterated elimination of strictly dominated strategies. It says that do elimination repeatedly until no more elimination are possible. When no more elimination are possible, then we have the maximal reduction of the original game, and we can just find the solution, Nash equilibrium in this case. Of course, if there is only one cell, then we are done essentially. If not, we need to find the Nash equilibrium. So let's consider, for example, this prisoner's dilemma. So you can say that here, so let's consider player 1 and player 2. So you can see that player 1 here, D, like U is strictly dominated by D. Why? Because if this person is doing L, then if you do it D, then you get 5 versus 3. And if this person is doing, the second person is doing R, then you get 1 instead of 0. So U means essentially a loser strategy. And a loser strategy can be removed. So you will just remove it. Now, you have the game with this one. This is essentially the reduced game. So in the reduced game, now you can see that here, L and R. For this guy, I mean, this person is only taking D. This person is taking L, it gets 5, it gets L, it gets 1, and if it gets R, it gets 0. So this is also, R is a loser strategy for player 2. So that can be eliminated as well. So we just get essentially DL as the one that essentially is a possible Nash equilibrium. I mean, you can always, it's good to double check to make sure that it is a strategy. I mean, it is a case, but in this case, when you get 1-1, essentially by definition, you are in a good shape. So this is the way that you can do it and make everything faster, essentially. So this is essentially the main theorem that we have. The Nash equilibrium of, so when you are we are okay. So this is the trick essentially. If you eliminate a strictly dominant strategy, good, then the reduced game has the same Nash equilibrium as the original. But you need to remove essentially a strictly dominant one. If they are just dominant one, not strictly, you may lose some Nash equilibrium during this process. So at least the set is not the same. Still, you might use it to find a Nash equilibrium, but the set is not the same essentially because you could use it as, because the other one was essentially equal. And if it was equal, it means that you could actually use that one for some cases. So whenever there is this kind of strictly dominant strategy, you can remove them essentially to have the things. And as I mentioned, because of this theorem, because the Nash equilibrium of the original game should be equal to the Nash equilibrium of maximally reduced game. So if you consider start from this one and you come to here, because we removed only a strictly dominated one, then this is the case that happens essentially that this one, the set of this set and this set should be this essentially equal, the set of Nash equilibrium. And it means that DL by definition now should be Nash equilibrium because there should be a Nash equilibrium for this game. And the only possibility is DL. And again, this is for a strictly dominated case. If not a strictly, this then the set are not equal. And you can think about it, what will happen in the weakly or very weakly case if it is dominated. In some sense, you are, if a very weakly case is that in some sense, yeah, this dominates this one, but if you remove it, there are some Nash equilibrium that you may lose essentially. So strictly dominant is dominated is very important here. Good. So another interesting thing that I mentioned, so everything that we talked so far about the pure strategy, but actually it might be the case that this happens for mixed strategies as well. And that's the thing that we want to discuss. It might be the case that SI is not strictly dominated by any pure strategies, but it is dominated by mixed strategies, and still you can remove it. So these are, again, special cases that can happen, and it is very interesting. So consider this game. This is essentially 3x3, like two. You have two players, 1 and 2, and each of them have 3 essentially actions or 3 pure strategies. So in the first game, if you see, R is strictly dominated by L. So let's consider R and L. So if so, I want to say, I mean, R, like essentially L dominates R, or R is dominated by L. So to do so, again, we consider L and R, and then we take the actions of the other person. Here, S minus I would be just the action of the others. In general, you should consider all strategy profiles of all actions of others. Like it might be, if there are two players, you need to consider three players, then you need to consider many more, essentially, this matrix. But this, again, you can do it in polynomial time, and the running time is not bad. So you will consider in two-player game, you consider two strategies, and it is order n, essentially. If n is, again, the maximum number of moves of both players, then you need to go through these two things and check it. So the running time is actually very good. So of course, to see whether one strategy, one dominates the other, if there are n by n, essentially, how many pairs should we take? I mean, to see whether one essentially dominates the other one? So n choose two. Because all two people here, you can see whether one dominates the other one. So n choose two, which is essentially order n to the two. You might think about it. I mean, this is a computational game theory. Can we do anything better than that? And these are the things that the people actually, these are very interesting things. And the people will think about it. There are papers even about those type of things. That can we do, for example, better? Can we find, if there is one which dominates the other one, in terms of at least pure ones, can we find in a faster way? Because one naive way is that you will consider any n choose two, and then for each of them, you are paying order n to check whether one dominates the other one or not. So the running time would be order n to the three. But think about it, can you do anything better? And again, these are some of the things that the people actually, you can think about it. And these are similar, I mean, problems essentially in algorithm. If you go for geeks, these are the similar problems that they are essentially improving the running time, and etc. And think about it, see whether you can get to anything, or there might be some papers there. You can check, see whether there are any papers, and possibly you may want to also implement this one in your algorithm, because that is something that would be helpful to get a better running time for you. But anyhow, so consider L and R here. So you will see that here, if this other person is doing, the first player is doing U, then you will get 3 versus 0. If it is M, then it is 1 versus, sorry, this is for first player. To see this one, let me change the color. Yeah. So if doing U, this person is getting, in L you get 1, in R you get 0. If this person is doing M, in this thing you will get it 1, you get 0. And if it's doing D, again, get 1 versus 0. So in all cases, essentially, R is a loser strategy. So in that case, and it is strictly dominated by L. So in that case, it means that we can remove L. And note that it is not the case. For example, R and C, if you compare them, it is not the case that, so if you consider R and C, so in this particular case, this R is not only dominated by L, but also dominated by C. Because if you see, the C things and L things are the same, essentially, for this guy. So also C dominates R. But anyhow, R can be removed. Now, in this case, if you consider it, if you consider U or D, so let's consider for the first player. So if you consider M, so M versus U. M versus U, so this person gets, essentially, if this person is doing L, he gets 1 versus 3. So U essentially is better off. But if this person is doing this, like the second player is doing C, then he gets 1 here versus 0. So here, U does not dominate M, because some cases M is better. What about the other case? What about D? D also does not dominate, because here, essentially, it gets 1 versus 0 with M, and here it gets 1 versus 4. So none of U or D dominates M alone. However, we can consider the mixed strategies. Consider half U, half D. So let me clean everything here. No, we can just. So let's consider half U, half D versus M. So this is a mixed strategy. This is half U, half D. So in this case, you can say that if this person is doing L, like this is the first player, this is the second player. So if the second player is doing L, then it gets half U, which is half 3, plus half 0, which would be 1.5, which would be greater than 1 that M gets. What about if he's doing, if they are, this second player is doing C? In this case, it gets half 0 plus half times 4, which would be 2. Who would be, again, more than 1 that you will get it? So in this case, there was none of them in the pure sense, essentially, that was answering your question, that none of them in the pure sense could dominate that. But essentially, if you consider the mixed strategy of them, in some sense, the mixed strategy would be some kind of weighted average. Here, the average essentially putting the weight 1/2 and half. Then this weighted average actually can dominate M, and thus M can be removed. Now you can see that we are reaching to this game. And in this game, we are in a, I think there is none that can be dominated. Why? If you consider U versus D. D cannot dominate U because in this case, if it's L, then gets, this gets 0 versus 3. And U cannot dominate D because also this is, here is 0 and this is 4. The same thing for L. So if you are doing L, then so if you are doing L, like L versus C. So L versus C here, I mean, yes, we are dominating here, but like here, 1 versus 1. And here, essentially, 1 versus 1 as well. So there is no one that strictly dominates the other one. And note that to have the same set of Nash equilibrium, we only consider the, we can only consider the strictly dominated versions. You can think about what will happen if we are talking about the weakly dominated things. Whether in that case, that theorem is still this theorem that we talk. So you can think about it, if instead of strictly dominant, we will talk about weakly ones, whether this theorem is correct or not, or where does it break. If you consider very weakly, then it is not correct, because then you are losing some strategies, because two things were equal, the set at least not equal. But you can think about the weakly one, see that if it is weakly, what will happen essentially. Can we lose some? That would be a good exercise, actually. Good. So let me do this. Good. So, I mean, so far we talk about, I mean, again, games, the different solution concept that we have it, and the representation by normal form games, and how can we get some different solution concept that you have been so far already. Essentially, Nash equilibrium, or this version of Epsilon Nash, or Pareto, optimal, and there are some other things that we will discuss later, like correlated equilibrium, etc. But one other thing that was the case that, I mean, we were discussing before. So when we are talking about the Nash is good, it's a stable. But generally, we want to get some stable, essentially, settlements that somehow maximize the utilities of the players. So you may think about, like, for example, you want to maximize the sum of the utilities of the player. So not only you want a Nash equilibrium, which is a good settlement, but also the one that, or like Pareto optimal, but you want to find that in terms of, you're not losing that much in terms of utilities. If you remember this battle of SXS game that we had, it essentially football versus house and wife and husband, between football and opera, we had this case that yes, we could find a Nash equilibrium, but in both cases, actually, the payoff that we got, it was less than the some other things. So this is the idea that we were talk with the concept of price of anarchy. And we want, this is the price of anarchy. In general, this is that if we are doing Nash, how much we are losing comparing to optimal solution. And here by optimal, generally, a reasonable thing is to consider the sum of the utilities of all players. There are some other optimals that we are considering. So we will talk more about this, and in general, this one and the Brazos paradox, that's another one that is very interesting, and we will talk next session on that.